go, that's that side done. I haven't joined the other side. Where's the other side gone? 13 dynamic part 1, 11 no, through to 11 50. Settings, that's fine. Allow recording, download, save. Dynamic part 1, join session. Right, that's the other side started. Start recording, enable. Right, okay. Pull that down. That one there. Where's the other side? There. And share application screen 2, share, right. Hopefully that will be good. Right, okay, that looks good now, right. Okay, click that, click that. Right, okay, 11 o'clock. Let's get started then. That one, make sure they're both showing up. Right, okay. So, right. Oh. Right, so, lectures 13 and 14. Bit out of order relative to the rest of them. I thought it was probably best to do the sequential logic lectures first because I didn't know what was going to be happening after the Easter break. So we did 15 and 16 first, and now we're going back to 13 and 14. So yes, we're going to be looking at dynamic logic today. Just checking my microphones are both on. Yeah, good. So yeah, we're going to be doing dynamic logic today. So all the way through the lecture, please do contrast this against the complementary CMOS and the pass transistor logic that we've seen before. Those were all static logic schemas, and so they've got a lot of things in common that you won't see in the dynamic logic lectures. So, dynamic... Oh, where's my pen go on? Yes, that's right. Okay. Yeah. Right. So, dynamic CMOS. Switch to the laser pointer for now. So when we were looking at our static circuits, at every point in time, except when we were in the middle of switching, the output was connected either to ground or VDD via a low resistance path. So in our complementary CMOS, there was a single level of logic going from our output through the source and drains of transistors up to VDD or down to ground in our complementary CMOS style, right? In our pass transistor style, we expect that our inputs are some way back along the levels of logic connected to VDD or down to ground, and so we provide the connection to ground or VDD through our inputs with our pass transistor style. Okay? Conversely, in dynamic circuits, we rely on temporarily storing the signal values on the intrinsic capacitances of high impedance nodes, right? So if you imagine your you've got your pull-up network and then your pull-down network with CMOS. They're connected to the output. There is going to be a capacitance at this output, right? What we're doing with dynamic logic is we're storing the signal value on this capacitance here, right? We're not necessarily going to have a connection to VDD or ground at one moment in time. We're going to rely on this capacitor storing the value for us, right? Specifically, what we do, our pull-up network gets replaced by a single PMOS transistor called a pre-charge transistor, which will charge up this capacitor. And then we have a standard pull-down network plus a gating transistor to discharge the capacitor if need be. If we want a high output, this PDN must stay off so that we don't discharge this capacitor, right? Because we have just a single PDN, we don't have a pull-up network. Our PDN has N transistors for an ideal function, plus we've got these two transistors here. So we only need N plus 2 transistors compared to the 2N transistors for complementary CMOS, right? Yet it will still give us a very high output voltage, unlike our pass transistor logic, which only requires N minus 1 or mostly sometimes it needs a few more. So somewhere in the order of N transistors for our pass transistor logic, right? Yes, Ziran.
Why do we need another NMOS under the pull-down network?
Right, yeah. So we're going to see that on the next slide. Okay?
Okay.
So how we design a dynamic gate. So imagine we're trying to implement the function AB plus C knotted, right? Obviously, if we were doing this in complementary CMOS, we would have our A and B in series, and then that in parallel with our C. And then on the pull-up network, we'd have our C in series with the not liking me at the moment, in parallel with our A and B in parallel, so A, B, C, C, A, B, right? So that's what we do in our complementary CMOS style. And there's our output. What we're going to do is we're just going to take our pull-down network down here. We're going to insert that in where it says pull-down network. And then we're going to add these two gating transistors, the pre-charge resistor, these two gating transistors, the pre-charge transistor and the evaluate transistor. When our clock signal, so dynamic logic fundamentally must be sequential in a sense because it's got this clock signal. When our clock signal is low, this MP turns on and it charges up CL, right? So that happens while the clock is low, right? If our pull-down network was on at this point and we didn't have this evaluation transistor, then we would have a short circuit all the way down to ground, right? And this would consume a lot of power and it would most likely heat up toast our circuit. So we must make sure that while this pre-charge transistor is on, even if the pull-down network is on, we cannot get a path to ground. So that's why we have this transistor at the bottom here, right? So we've got this transistor at the bottom here turning off the path to ground while the pre-charge is happening. Then, when our clock changes to 1, this MP turns off, so we are no longer pre-charging CL, and so it's storing that high voltage on CL. At this point, because our clock has gone from 0 to 1, ME will turn on, meaning there's a path here. If our pull-down network is on, then that high voltage that is stored on CL will get discharged through the through the pull-down network, through the evaluate transistor down to ground, and so this will return to 0 volts. If, on the other hand, our pull-down network is off, then we will maintain the voltage on CL because there won't be a path through the PDN, and so this will stay at 3.3 volts or whatever our VDD is. Okay? So this is the standard operation of a dynamic gate. You charge up using your pre-charged transistor right at the top here. And then, while your clock is low, and then when your clock goes high, your pre-charged transistor turns off, your evaluate transistor turns on, and then if your PDN is enabled, so either C is high or A and B are high, then it will discharge the CL, and hence you'll get your low voltage, right? So yeah, that was just some of these showing up, right? So let's look at this on a graph. So here we've got our signal was being pre-charged at the start, our clock was low, and so our MP was on and our voltage was at VDD. So in this particular circuit we've got 2.5 volts is VDD. Okay? Then we say that both our clock and our input signals all go high. So this goes 0 to 1, 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 and obviously this goes 0 to 1, right? When that happens, our pre-charged transistor turns off, our output is no longer connected to VDD, and because all of these are enabled, there is a path down to ground, and so our output discharges its load capacitance, CL, down to here, and it gradually, it's an exponential as always, and it gets down to here. And so when it gets below our threshold point, so I'm going to put a threshold point here on it, in this region here, the output is considered as a logical 0, whereas back here, the output would have been considered a logical 1, right? If, on the other hand, one of these hadn't transitioned, so imagine that this transistor here had actually been 0, then our output would have oscillated a bit, dropped a little bit, stayed there, and then charged back up to 2.5 volts. So it would have stayed at a logical 1. Right? So let's define some timing metrics and some voltage metrics. Right. So here we've got a 6 transistor circuit. So we've got our 4 inputs plus our evaluate and pre-charge transistors. So n plus 2 is equal to 6. Therefore, n was 4. We've got 4 inputs. If we have, we've got a question. At the rising edge of the clock is when we will evaluate, will either hold the value to 1 or drop to 0. This sounds like a D flip-flop. Is there any connection between the two? Sort of. It's mainly just that our logic is, dynamic logic is fundamentally sequential because we've got this clock signal timing everything, right? Dynamic logic is always sequential, unlike our CMOS and our pass transistor logic, which is purely combinational, and we have to add in extra sequential stages. Okay, so it sort of combines the functionality of the sequential side and the combinational side in the dynamic logic, so it's more efficient in the fact that we don't have to then add D flip-flops if we don't want to, right? But obviously there's other issues with it. So yeah, in a sense, yes, but purely because dynamic is on its own sequential. D-type flip-flops are just another type of sequential logic, right? So yeah, let's look at our voltage metrics first. We've got V on high, so the voltage that we get to if we've got a output of 1. Well, we get a full 2.5 volts. Just like with our complementary CMOS, we go all the way up to VDD, right? Unlike our pass transistor style, we don't necessarily drop voltage over transistors, right? V on low is 0 volts. If we get a connection directly down to ground, we will go all the way down to 0 volts. Again, unlike our pass transistor style, we get a full rail-to-rail swing with dynamic logic. Then we've got our VM, our midpoint, our crossover point, right? Unlike complementary CMOS, where VM is VDD by 2, because we've got the competition between our PMOS and our NMOS transistor, with dynamic logic, just like our pass transistor logic, the crossover point is the threshold of the NMOS transistor, because it's when we're able to turn on an NMOS that matters. Just like with our pass transistor logic, if we had A, B and C, like that, B, C, the point at which these two transistors start to conduct in pass transistor logic is VTN, the threshold of an NMOS, right? Similarly here, the point at which these start to conduct is VTN, right? And so if we know that our midpoint, our crossover point, is VTN, then we know that our noise margin on the high side, so the difference between our on high and our midpoint, is going to be VDD minus VTN. So we've got a large, very large in fact, noise margin on high output signals. However, our noise margin on low output signals is only VTN, because it's the difference between the threshold point and V on low, which is 0 volts. So, unfortunately, our noise margin low is quite bad. That's not actually a problem though for dynamic logic, because it's actually our high output signals. Delete that. It's actually our high output signals which are more susceptible to noise, because our low output signals, if we disturb our output, so let's add plus 0.1 volts here, that 0.1 volts is going to just discharge directly down to ground if we're aiming for a low voltage, right? However, if we weren't aiming for a low voltage, if we were aiming for a high voltage, so we started off with 2.5 volts here, and we took off our 0.1 volts, it would stay at 2.4 volts there, because there's no path up to VDD, it won't charge back up to VDD, but because we've got such a large high noise margin, it's not actually too much of a problem if this discharges down to 2.4, 2.3, 2.2, 1.5 volts. If we say maybe VTN is 0.6 volts, it can even go all the way down to 1.2 volts if it likes, and we'd still be getting a high because our midpoint is so low. And so it's actually beneficial to us that we've got a big noise margin high and a small noise margin low. So that's our voltage characteristics. What about our time characteristics, our propagation delays? So obviously we've got a high to low propagation delay. We have to discharge this CL here, right? So from the midpoint of this signal, somewhere about 1.2 volts. Oops. I've lost my pen. So from the midpoint here, about 1.2 volts. To the midpoint here, about 1.2 volts. So let's do a simulation in some piece of circuit simulation software. Maybe it's the IBM process this time. And we get 110 picoseconds out of it. Okay, so that tells us how long it takes to discharge our output through 4 transistors, right? So that's for a 4 input gate, we've got 110 picoseconds maybe. However, what's going to be our propagation delay for the low to high? So if one of these is 0 and we're not discharging it, how long does it take to get from to the high from the rising edge of the clock signal? Well, it's already high because we pre-charged. So we've got a 0 low to high propagation delay, right? This is great because it means that we don't have to worry about charging our signal up, about the sizing of the PMOS transistors to make sure that we get a balanced propagation delay, because our low to high is 0 all the time. So we only have to worry about the delay on our NMOS pull-down network, right? We don't have to worry about electron-hole mobility differences. Actually, I just want to have a look at the notes I've got here. No, that's not the one I wanted. Where's the... Sorry, just a sec. I didn't mean to turn that one on. Should present a view. I had a note on what VP was here. Yeah, okay. Oh well. We'll worry about that later, if I need to. Right. Present a view. Right. So, but remember I said back here, if we disturb this output and we take 0.1 volts off of it, it'll stay at 2.4 volts. It won't go back up to VDD, unlike a complementary CMOS or pass transistor style, because it's not regenerative. If we lose a bit of voltage here, it stays lost until our next clock cycle, right? Meaning if we lose all the voltage and we go all the way down to 0, just after our clock changes, we cannot get back up to 1 until our clock goes low again and we get back to our pre-charge phase. Right? If it goes low, so there's the output, there's the clock. If it goes low, it stays down here until the next pre-charge phase. Therefore, the inputs to all our gates can make at most one transition during evaluation, right? So if we imagine we've got our clock going high for its pre-charge, and we have our input which goes high and then low, our output is going to go low, and then remember, our output can't charge back up again, so it'll stay low, right? So you need to remember that we're only allowed to transition at most once. We cannot have any glitching in our logic, because if we have glitching in our logic, we will end up discharging our transistor at our output, and as a result we will lose the correct result. Unlike complementary CMOS and pass transistor styles, where it can recover from a glitch is now a functional error, not just a timing error, right? So let's see our CCMOS, our PTL, and our just check the time, yeah, and our dynamic. Right, with our CCMOS, our input glitches to high, our output glitches low and then recovers, right? For our pass transistor logic, and this goes all the way up to VDD. With our pass transistor logic, our input glitches high, our output starts off below VDD, glitches down to 0 and then goes back up to below VDD with our 1 VTN voltage threshold from our VDD. And again 1 VTN. Here we're always at VDD, right? And then ground. With our dynamic logic, our input glitches as long as it glitches above VTN, our output will go low and then it will stay there. It won't recover, and hence that one works, this one has failed, right? So we need to be very, very careful never to glitch. However, one benefit of dynamic logic is because the output can only transition down, it can't transition back up again. We know that if we put dynamic logic beforehand, then our current dynamic logic cannot see a glitch because the dynamic logic beforehand can't transition more than once, right? So this is one of the good things about dynamic logic. Dynamic logic will not produce glitches, so it cannot cause glitches in dynamic logic, right? So we cannot have glitches, we can only have one transition at max. Power, right? So remember when we had our complementary CMOS circuits, we said probability of a 0 to 1 is the probability of a 0 before multiplied by the probability of a 1 afterwards, right? And so if for a NOR gate like this one, the probability of 0 is 3/4. The probability of a 1 afterwards is 1/4. Multiply those together, you get 3/16. So that's the probability of consuming power in a particular transition cycle for complementary CMOS. Right? Now let's think about our transition probability in dynamic logic, right? So probability that the output is 0. Well, we've got 3 zeros in our output, so there's a 3/4 probability, given that the probability that A is 1 is a half and probability that B is 1 is a half. We've got a 3/4 probability that the output discharges down to 0. probability that afterwards the output is 1. It's 1. Why is that? Well, remember, this is dynamic logic. Where is it? No, it'll be this one. Right? After every discharge, regardless of how it managed to discharge, regardless of what the inputs are, after every discharge, there is a pre-charge cycle, because it doesn't know what the next input values are going to be, so it has to charge it back up to VDD. Right? So if we see a 0 on any one cycle, on the next cycle there must be a 1, and it must charge up. So the probability that it was a 0 before, as we said, was 3/4. The probability that there's going to be a 1 after, given that there was a 0 before, is 1, because it must recharge through that pre-charge cycle. So therefore, the probability of a dynamic gate switching is much higher, right? Therefore, the dynamic power is much higher, because we always have to charge back up to a 1 if we discharge down to 0. Also, with a NOR gate, if we compare it to a NAND gate, for a complementary CMOS, we would get 1/4 times 3/4, and so we get exactly the same power for a NAND as we do for a NOR, right? However, for dynamic logic, it would be 1/4 times 1, meaning a probability of 1/4. A NAND gate is going to be less power consuming than a NOR gate in dynamic logic, compared to complementary CMOS, where it's the same power, right? In fact, if you write out your truth table verbosely, your dynamic power is going to be proportional to the number of zeros in your truth table. Alright, just check I didn't have any raised hands, did I? That's what I saw in the message. No, it looks fine. Okay, right. Right, so dynamic component of switching activity is higher in the gates, because the probability of going from a 0 to a 1 is the same as the probability of going to a 0, because we must always recharge to a 1. However, the glitching component, dynamic component, the chance of a signal changing multiple times during a clock cycle, is 0, because we define that dynamic logic must not glitch. Right? So these are all the base level aspects of dynamic logic. Let's start to have a look at some of the more complicated annoyances that happen, just like with complementary CMOS, just like with past transistor logic. Things are never as simple as just don't glitch, right? There's always going to be other issues, right? Principle 1 is charge leakage, right? Remember we said our transistors are leaky. A transistor that is off is simply is defined by the fact that R on by R off is on the order of 10 to the 5. Right? The resistance when transistors are off should be about 10 to the 5 times the resistance when the transistors are on. But that still means that current is flowing through these transistors. It is still leaking through all these transistors. And especially if we start using low VT transistors, that might go down to 10 to the 4 or 10 to the 3 as we start to reduce our VT here, right? We've got leaky transistors, and so our voltage won't just stay up at VDD. It'll gradually start to drop down, right? It'll gradually start to discharge, not only through the transistors themselves from source to drain, but also there is a diode from the source and the drain back to the body, and that diode is slightly leaky, and so it's going to drop some current there, right? And so we're going to see that this CL won't just stay perfectly at VDD, it's going to gradually drop down throughout the evaluate stage, even if our transistor is off. And so we need to make sure that if this is our, drew a very bad line there, if that is our VTN, we need to make sure that that discharging doesn't ever drop below VTN, right? And so there's going to be a minimum time between pre-charge phases. Or, sorry, a maximum time between pre-charge phases. If there's a maximum time between pre-charge phases, then that means there is a minimum frequency on our clock signal. We've got a minimum clock rate of a few kilohertz. We cannot just switch our clock off and just leave the circuit as is. We have to occasionally reevaluate our circuit if we want to maintain our output signal, right? Obviously, we can just turn the entire circuit off and say we don't care what our output signal is. But if we want to maintain our output signal, we must, at the very least, maintain this minimum pre-charge frequency and this minimum clock frequency. So we see, yes, we've got our clock goes high and then low. While our clock is high, our pre-charge transistor is off. Our output decays exponentially until our clock goes low again and our pre-charge transistor turns on. Right? We had the same issue of reduced voltage with our pass transistor logic. Who can remember what we did to solve this issue with pass transistor logic? By all means, call out. No? No one? Go have a look at the pass transistor lectures. We use a keeper transistor. Just with our, as we did with our pass transistor logic, we introduce a keeper transistor so that if our voltage tries to drop, but it's still above our threshold, so VTN, VDD, if our output voltage tries to drop, our keeper will provide current to push it back up, right? And so we have our, so we've got our keeper transistor. Obviously we need an inverter to invert the output to, because if this is a 1, this must be a 0 to turn this keeper transistor on so that it charges it back up to VDD. And then we have a pull down network which discharges down to ground. Obviously we know that at the start of each clock cycle this node here must be a 1. Therefore we know that at the start of each clock cycle this keeper transistor will be on, and then if we try to discharge down to ground, we've got a direct path from VDD to ground, meaning that these two transistors here must be able to overpower this keeper transistor, right? If we add in a keeper transistor, it becomes ratioed logic, okay? So we need to make sure that that keeper transistor is as small as possible, and we size these NMOS transistors so that they can easily overpower the keeper transistor. And the bigger the keeper transistor is, compared to these NMOS transistors, the harder it will be for them to overpower the keeper transistor, and the slower the transition is. So if we draw our, so let's us presume that these are both 1. Our clock starts off low and goes high. We draw it with, let's say, in this one we've got MKP equals 1, so the size of it is 1, and we've got N KP, not KP, and the N are going to be NA, and then B are going to be, let's say, size 2, and we're going to see it goes down that fast. Whereas if we have NAB equals 1, it goes down slower because it's harder for these two to overpower the keeper transistor. And then let's add another case where we say MKP equals 2, so now we've got a bigger keeper transistor, and we see that it just sort of goes like that and doesn't actually get down to ground, because our keeper transistor is stronger than our pull down network in this case. It's ratioed logic if you introduce a keeper transistor. Okay? So always be careful if you introduce a keeper transistor, but what it does mean is that there is now no longer a minimum clock frequency, because even if you don't set the clock low to activate the pre-charge transistor, if the output is high, the inverted output will be low, and hence the keeper transistor will stay on and it'll keep the output at VDD. One other benefit of this scheme is we've now generated the knotted version of the output, and then we will see next lecture why having that knotted version of the output will be quite beneficial. So if you imagine you've got, well, first thing is just the ability to use it in, say, AND gates, but also we'll see why having an inverter available is quite helpful to us. Right? But that will be next lecture. Right. Do we have any questions? Right, Ziran, go on.
I have a question about the slide 3.
Hello.
Right, we've got two people in different chats a moment, so if Ziran can start first, and then I'll see who it is in the other chat, okay? So Ziran, start first, and you said slide 3.
Yeah. So we have this issue when the pre-charging phase is passed, the output voltage might drop down below the threshold voltage, which will introduce a 0, but what we're looking for is 1. So what if we implement the pull-up network? So instead of just put a pull-down there, is that gonna work?
So you're saying what happens if we have a evaluate transistor up here, then we have a pull-up network.
Yes, and a clock
and
connected
then
MOS.
Pre-discharge transistor like that.
Yeah.
Right. So here we've got exactly the same scheme as our dynamic gate, but just inverted. So now we've got pull-up network, right? We're going to pre-discharge down to 0. And then we evaluate with our pull-up network. Remember, these transistors are also going to be leaky, so we're going to gradually, exponentially decay up like that. Okay? Right? So just as much as in our pull-down network, these transistors are leaky, or they might glitch, and that will cause our output to discharge. With a pull-up network case, the transistors can still be glitchy and they can still be leaky. Well, they must be leaky because they're transistors, and so they'll actually leak voltage from VDD to our output capacitor, right? So that's why it's not beneficial to just swap it the other way around, because just as much as we can leak charge down to ground, we can also leak charge up to VDD, or well, leak charge from VDD, right?
The charging rate will be exactly the same as the discharging rate as the previous case, right?
Because our well, if we presume there's no difference in electron hole mobility,
Yeah.
then yes, that'd be true. However, if we presume there is a difference in electron hole mobility, what is the disadvantage of having this scheme as opposed to this scheme over here?
You would charging faster, so your zero will you will have a smaller threshold, right?
So it's not well. So it won't have a smaller threshold because if we go to this slide, our VM will change to VTP, right? So the threshold over here will just be VTP, and this will be, or sorry, it'll be 2.5 minus VTP over here, VTP being like 1.9 volts. So we'll end up with a high noise margin low instead. So it's not an issue because it's the noise margin over this side away from the pull up or pull down network that we care about. So that's not an issue. But if we have a difference in electron hole mobility, either this pull up network needs to be much bigger than this pull down network would need to be because PMOS transistors are inherently slower, or we would just have a slower dynamic gate than with a pull down network, right? Presuming there is a difference in electron hole mobility, because the CL won't change. All that will change is, compared to the pull down network, the pull up network either must be bigger physically, we must have 2 times or 3 times sized PMOS transistors, or they'll have a higher resistance, and so charging up the CL through the pull-up network will be slower. And so for that reason, we always use a pull-down network scheme. Does that answer your question?
Yeah. Well, the second one reduce the power consumption. Because
with this one over here?
Yeah.
No. No, because actually no, let me think about that. So the static components aren't massive in dynamic logic generally. Generally the biggest thing you are concerned about is the dynamic power, because the dynamic power is so high in dynamic logic. If you've got so if we look back at this slide, if you've got a NAND gate where we've only got 1 0 in the truth table, and so we rarely discharge, it's better to have the scheme with a pulled down network, because most of the time we will stay at 1. Whereas with a NOR gate where we're discharging a lot, it's better to have a pull-up network in terms of power, because we're going to only rarely be charging back up, right? And then discharging down again, right? So yes, if you're trying to aim for low power, then you want to aim, in your dynamic design, then you want to choose either a pull-up network or a pull-down network, where if your output normally stays high, you choose a pull-down network. If your output usually stays low, you want to choose a pull-up network. However, if you want low power, you're better off with complementary CMOS anyway, because the chances of transitioning are lower in the first place. Does that make sense?
Yeah, that makes sense.
Right, okay. From the other chat, I presume it was Varun, I'm not sure, but...
Yeah, Scott.
Yep.
Can you explain the low to high transition being 0 with respect to the graph in slide 5?
Right, okay. Is there some space here? Right, okay. So let us presume that we've got an inverter because it's the simplest gate to look at, right? So we've got our pre-charged PMOS transistor. We've then got our input NMOS transistor, and we've got our evaluate. So clock, clock. I'm writing this very badly. Inverter. There's our output with its capacitance on it, right?
Okay.
So if we presume that our input is 1, what we'll see is that we'll have our clock is low, it'll go high, and then our output will discharge. This is obvious, right? And then we've got our propagation delay from the 50% points, right?
Mm-hmm. Yep.
On the other hand, if our input is 0, right, we'll see that our clock goes high. Obviously, it was pre-charged when the clock was low. And so from this 50% point of the clock, how long does it take for the input to be high?
Okay, it's almost instantaneously.
It's
I mean,
exactly instant,
Okay.
right? And so this is the key point with the key point with the timing of the dynamic logic, right? Because the input is because the output is already charged, the time from the 50% point of the clock signal to the output being high must be 0, right?
Okay.
Quickly from the other chat, the question I'm answering at the moment is why is the TPLH, so the low to high propagation delay, 0 nanoseconds, right? That's what the question was, why is that the case? And the case is because we've got our output already charged at the start, okay? So the time for it to go high, because it's already high, is 0. Right, now we've got a question from Spiros. At the rising edge of the clock, no, sorry, seen that one. I answered that earlier. We have 3 different techniques to implement the same function, so what are the things to consider when choosing which technique to use? Right, so this is actually on the last slide, so I'm just going to quickly pop over to it. Please ignore all these. Right, so, just going to quickly show you this slide. Don't consider too much about it at the start. So we've got our complementary CMOS, we've got our complementary pass logic, so I'm not showing simple pass transistor logic, and we've got our domino dynamic logic, so domino just means dynamic logic here, and we're saying for 4-input NAND, what are the metrics? So first thing, for our complementary static, we've got 2 N transistors. For our complementary pass logic, we've got 3N plus 2. And for our domino, we've got N plus 4 by the looks of it. Yeah, N plus 4 transistors, right? So if you just want to improve your area, domino is the best thing to do. If you just want to get as much functionality in a small space as possible, just go for domino logic, especially since you don't need to add in D-type flip-flops. For ease of use, complementary CMOS is generally very, very easy to work with. So we don't need to worry about voltage degradation over multiple stages of logic, or keeper transistors, or regeneration with the insertion of inverters. It's very easy to use, so if you just want to make your design task easier, you would choose complementary static logic. If you've got some other considerations you need to put in, so like there's something else that you consider, oh, I need this as well, then maybe you might want to go for complementary pass logic. Domino dynamic logic, on the other hand, is very, very difficult to design, so you're not going to choose that if you just want to design the chip as quickly as possible. Yes, domino, we'll see what domino means specifically, but just presume it's dynamic for now, right? I'll go into more detail next lecture. None of these are ratioed unless, and the big unless, is the keeper transistor, right? If you add in keeper transistors, then it becomes ratioed, but no, in general, none of these systems are ratioed. If you want to optimize for performance, dynamic logic is the best, because you've got much less intrinsic capacitance sitting on your output node, because you've got the zero low to high propagation delay. The delay of dynamic logic is generally better than any of the others. Pass transistors, because there's so many stages of logic between your VDD and your output, normally that one ends up slower than your complementary CMOS logic, and so this one will end up with a worse performance but has other benefits. And the same thing with pass transistor logic. It has other benefits to it, but it's not going to be the fastest system. Complementary static gives you a relatively good delay while being very easy to design. As for power, your complementary CMOS is generally the best in terms of power. Complementary pass logic is particularly bad because it's got a lot of transistors present, but if you go to pass transistor logic, that's very similar to complementary static logic. As for domino logic, it's not quite as bad as complementary pass logic because it's got not as many transistors, except your power is very dependent on your clock speed, and your clock speed is generally quite high because we're generally aiming for high performance with domino logic, and so this ends up being 5, 6, 7 much higher values than any of the others, right? Because we get so much dynamic power consumed from our transitions. So in general, dynamic logic, low numbers of transistors. The only thing anywhere near comparable is pass transistor logic with just one-sided, not complementary pass logic. And it's got very, very low delay, meaning that it's going to be fast logic. However, the ease of use and the power are not great. Right. Right. What does it mean for a system to be ratioed? Right. If I just pop back here. Didn't mean to do that. Give me a sec. Back to here. Shift F5. Right. So remember when we saw our keeper transistors in both the pass transistor logic section and now in the dynamic logic section, we saw that how am I say this? There we go. Right, we said that actually we need to make sure that the logic, like we've got this keeper transistor which is holding the output high. We need to make sure that our output, our pull down network, is able to overpower that keeper transistor, right? We also saw this with the design of the sequential section. We saw that, with the bistable circuit, saw that we need to overpower that feedback loop between the two cross-coupled inverters, right? So either we cut it or we just overpower it, right? With our sequential logic, right? The point here is that the bits that needs to overwrite it must be more powerful than the bit that's holding it there, right? And that's what this graph over here was. If we've got a very strong pull-down network and a weak keeper transistor, it'll very quickly overpower it. If we make our pull-down network weaker relative to our keeper transistor, it'll be slower. And then if we make it too weak, our pull-down network will not be able to overpower the keeper transistor, and so we won't be able to get down to our 0 volts, right? So we need to make sure exactly that the ratio of transistors, like the ratio of resistances on our pull up and pull down, must be set such that the pull down can overpower the pull up. Okay? So that's what it means by ratios. We need to make sure that the ratio of the transistors is correct in order for it to function correctly, not just for timing purposes. Right. Do we have any more questions? Right. Dynamic logic, question was, is domino ratioed then? Dynamic logic, if we put a keeper in it, is ratioed, right? And we need to be very careful of our ratios. If we do not put that keeper transistor there, if we just design it like we did here without a keeper transistor, we don't it doesn't become ratioed, but at the same time we have a minimum clock period, a maximum clock period and a minimum clock frequency if we don't have the keeper transistor, right? So it's a design trade-off. Do you want to be worried about your keeper transistor and getting your ratios right, or do you want to be worried about your minimum clock frequency? And depending on your particular design, that will change, right? As for if there's any specific applications that where one technique is better than the other, generally the place you will find dynamic logic, if we just look back at the end of the lecture, the place you will find dynamic logic is purely dictated by this number here, right? Because the delay is so low relative to the other schemes, we see that dynamic logic generally tends to show up in adders and multipliers in the critical path of your circuit, specifically in the arithmetic logic units of CPUs, or the anything which is very easy to design, because it's not easy to design dynamic logic, but things like arithmetic logic units, multipliers, where it's very simple logic that's multiplied multiple times over. The barrel shifters are also another example. Something that's easier to design and needs to be fast will end up with domino dynamic sequential logic, right? On the other hand, things like branch prediction units, which are very, very complicated pieces of logic with very, very weird paths through them and lots of glitches, they will go for complementary static logic, right? Generally because, not because they don't want to be fast, they do want a very, very fast branch prediction units, but designing domino logic or dynamic logic which can perform branch prediction, because it's so hard, isn't really feasible. So they don't really have the option of domino logic if they're trying to do branch prediction unit, because it's so difficult. So therefore they go for the next best thing in terms of delay, which is our complementary static logic, right? What advantages does CPL have compared to the other two styles? CPL is a bit of a weird one. It's not used very much anymore. The benefits of it are the fact that you've got both the normal and the inverted version of the signal. And it's got a very, very regular structure compared to the other logic systems. So what we generally tend to find is that CPL tends to be used for either FPGAs or semi-custom ASIC designs, right? For FPGAs, having that inverted version of the signal, or another one is CPLDs are also quite common for this. Having that inverted version of the signal quite often is very, very helpful because you don't know whether your circuit's going to be inverted or not. Also, having the regular structure of CPL logic where you just have to change the routing around means that implementing an FPGA with a very high density is very, very easy because you don't know what your logic function is going to be at manufacturing time, so you need to provide as much programmability to it and as much and make it as generic as possible. So what we see, especially with FPGAs, is that they have a static logic block, right? We call them configurable logic blocks, and then we have something called a switch, right? Which multiplexes all the inputs to it, and multiplexes all the outputs from it, right? And so our configurable logic block might be made out of CPL logic, where it's static and it's very, very regular and highly compactable, without reducing the generality of the logic, and then we just configure what the specific inputs are. The other thing is semi-custom ASICs, where what you've got is you've got a layer of, you have what you call your logic layer, which would use, say, metal 1 and poly 1 and all the diffusion regions, right? And then on top of that sits the routing layer, which is maybe metal 2 and metal 3. What happens is this logic layer is fixed, right? It's always the same, and so you might have CPL cells inside that fixed logic layer, and then the customer, the person who's actually designing the chip, only changes the routing layer, right? So they say, okay, I've got all these cells down here, and I'm going to connect this output to this input, and this input to this output, and this output's going to connect over to this input. And so they configure the routing. The fabrication facilities provide a fixed set of CPL cells below the routing layer, and then that way you get what's called a semi-custom ASIC, which isn't as expensive to manufacture since you only need to build up the routing layer different to everyone else, and the fixed logic layer is the same for every single customer. It's not quite as performant, but you're able to get lower costs for your chip manufacturing. Right, so question from Spiros. For CCMOS, wouldn't we ratio it to balance the circuit? Yes, but that is a timing issue, not a functionality issue, right? When we say a circuit is ratioed, that means that we need the correct ratios on the transistors for it to be functionally correct. Obviously, depending on the ratios of the transistors, the timing will change for any circuit. However, that doesn't make the circuit ratioed because the functionality will be correct, it will just take longer to do it. Okay? Question from Zero. Where can we find the replay of the lectures? So I'm going to bring up a... Right, so this is the Blackboard Collaborate page. I'm just going to zoom that in a bit because it's not quite so clear here. Right, so here's the Blackboard Collaborate page. So there's the lecture that we're on at the moment. If you click this button here, which says menu, you'll get a sidebar pop up, and then we've got an option for recordings. then change the filter to recordings in a range and set it back to the 1st of April? Why has that not shown up? This was on here originally. Let's try the other one just in case. Collaborate. Recordings. Where did the recording go? That's odd. Where's this one? Give me a sec. Library. Where's mine? Okay, so I'm not sure what happened to lectures 15 and well, I know what happened to lecture 15, it wasn't on here, but I'm not sure what happened to lecture 16. I'll have to find what happened to that. But if you don't, for now, just use my YouTube channel because I'm streaming these all to YouTube as well. So if you need a replay, just look at the YouTube channel. Is there a link to... No, I don't know where it is. Okay. I'll see if I can find a bit better link. No, that's not going to work, is it? But yeah, yeah, just use my YouTube channel for now. I will get these uploaded to Blackboard at some point and then try and work out why this isn't recording when it should be, okay? But... there, right, yeah. I'll work out where those went to and see if I can stop them from disappearing, okay? Right, but yes, I'll send out a link to the YouTube channel just in case. Any other questions? No? Okay, we have overrun a bit, so if you do have any questions in the meantime, by all means just send me an email. There is a... where is it? There. So I have uploaded a quiz for you to give it a try on the sequential section. Please do have a go at it, check whether you understood what was happening with the sequential logic. I've given you, it's not going to be graded in any, well, you'll get like a mark, but it won't affect your grade at the end of the day, okay? So this is purely for your own, if you want to see how well you did, okay? But that is available if you want. Okay, so I will probably end it there. Are the marks going to be released before the exam season? Marks for the coursework. I am going to start marking Lab 2 soon. Lab 3, I'm going to wait until some of the extensions have expired before I start marking that one. So Lab 2 somewhat soonish. Maybe by the end of next week, but I can't promise that. That's sort of like, that's more of a goal rather than anything, but I'll try and get it out by then, but I can't promise anything. As for Lab 3, expect, 4th, add on 2 weeks, maybe by the 18th of May, that might be somewhat reasonable, I think. For Lab 3, given that I've got a lot of extensions to deal with as well. So that's the sort of region I'm looking at, okay? Right, I will leave it there then. Thank you for watching, everyone. I will see you next Tuesday. Bye. Alright. Right. Um,